Okay, my friends, let me just set you up right up front. This planet is in deep trouble, and we need to get free electricity without combusting anymore. I'm going to go into extreme detail. You see what this says? Muon neutrino, electron neutrino. The two of them together, it's a black and a white ball. When they hit heavy water, you get electron showers, and you get a sterile muon. We did this right here. That's the electron showers. There's a sterile muon. It came from light particles. Light divides. These are the particles they see at CERN and Fermilab. This is actually the Fermilab picture. This has no mass, but all the energy that has all the mass and just push. Here they are as photons. Here they are going into their electron showers and their sterile muon mode, which I just showed you before. See, muon neutrino goes into muon sterile, electron neutrino goes into a shower. There it is right there. Well, according to the story that they say from CERN and Fermilab, is that if you can get down to this electron and muon neutrinos, the energy of these neutrinos is a few hundred billion electron volts to a few trillion electron volts. Now remember, this is the physics of electron showers. I just showed you electron showers. Of this, there is no doubt. You see that? Electron shower. You see that? Electron shower. The black part is the muon. It goes sterile. You can see it. And then they come back together. We need to harvest this right here. And then we'll have all the energy we could ever use, because what happens is it's an energy increase. And why do I say that? Well, I don't say that. They say that. Here's what they say. Coming through low energy showers, very low, and then they start, and then you get the high energy, huge amounts of energy. So what energy did we start with for this laser to come through here? How many watts? Well, let me just put it this way. Let's say we started with 5 watts here. How many watts would it increase by the time we hit the high energy showers? Let's see what it takes to create the light, and let's see what it says. We know right now that we can get billions. Well, here it was again. Let me just be sure you understand it. I don't want to make any false statements. It comes through as a neutrino with a few hundred billion, a giga electron volts, to a few trillion electron volts. How much did we start with before we got those high energy showers? Okay, this is going to be quick and simple, the introduction, and then it's going to be complicated and long. Does an increase in brightness mean there is an increase in energy? Yes. Okay, now it says brightness and energy relationship. Brightness often refers to the amount of light or electronic radiation received from a source, which related to the radiant flux of intensity of emitted radiation. Blah, 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 blah. An increase in brightness generally means that the radiant energy emitted by the source has increased. So the radiant energy emitted by the source, in this case is the laser, that energy has increased. In simpler terms, if an object becomes brighter, it is radiating more energy. Well, what is the key now? If we know we have increased the energy because we could see the brightness growing like crazy, and we didn't do anything whatsoever, all we did was put it through a restriction, a Venturi. The stuff had to come through that, and in that case, all their fields had to crush together, and the black just keeps slapping it through there. So we didn't do anything whatsoever, and it increased its energy in brightness. That means we have increased its energy. How much did we increase it? It's astronomically. Astronomically. Okay, you made a statement. Extraordinary claims mean extraordinary evidence. Well, I just showed you that if you can increase the brightness, you can increase the energy. We started back here with light. Very little brightness. It started to get bright as it accelerated because it was forcing against every other field here. Its field had to push through. Well, its field is being sucked so fast that the particle is being sucked right out of the magnetic field. It's just incredible. The field is just like, anyway, like a jet fighter. Now, this, again, exceptional claim. This is subatomic nuclear explosion. I'm going to explain it in extreme detail shortly. The explosion created all of these fields to expose themselves. They're there, but you never would have seen them until they got slapped like in the face. And every one of these fields is just exactly like a Higgs field. Now, you see this layer back here? You see that? That's called reverse electromotive force. You see those waves? They're going backwards. They shouldn't be going backwards. They should be going forwards, just like the other one. The reason they're going backwards is from this explosion over here. That is like an atomic bomb. Well, it is. It's a subatomic bomb. And this is fission, where they broke apart, creating extensive amounts of energy. And this is fusion, where they came back together. So what have I shown you? Acceleration. I've shown you light as a particle. And it creates a wave as it comes through. You can see the particle was in the wave. I've shown you that the particle itself splits in two, which gives you the extreme energy in the neutrino phases. Because all the neutrino wants to do, the white one, is get that back to the black. When they're separated like that, that is your top end energetic reaction. That is the big one. That's the one they talk about giving you the major amounts up here and here, where the energy of neutrinos interacting, you can get from 100 giga-electron volts or so to trillions. And we are going to be up in that area. And a little tiny box you could carry around should be able to squirt just gobs of energy out. It seems. And the energy you put in your car has no weight, and so doesn't the white here has no weight whatsoever. That will have no weight whatsoever, zero. Well, it's got to have something, but I can't find it, and nobody can. They say it's not zero, but it's so small that nobody really can find it. I've seen where they weighed a car. It was I forget how much it weighed, but let's just go with 4,000 pounds. And it was totally empty of electricity. They drove it, filled it up with electricity. It still weighed 4,000 pounds. It didn't change, not even an ounce. They drove all day long, and it got down to almost used, like 500 miles or whatever they did with it, and it still weighed 4,000 pounds. They filled it back up, 4,000 pounds. They're just circulating those electrons around, and those electrons don't weigh anything. So if you use gas, for every gallon of gas is 6 pounds of material. 6 pounds, and then when it expands, it's just devastating to the atmosphere. There's just much combustion, way too much. And then when you get these huge wildfires and so forth, whew. So anyway, this is the only way out of this, is to be able to get free energy. And the only way to get free energy is to be able to have something like this, not some big, gigantic facility. You need something you can carry around in your hand, just like this, cheap and simple. Anybody could have it for the masses. All right, now let's, I guess, get into this pretty deep. All right, like I said, we're scrubbing through space, and everything, there's huge fields, and we're scrubbing through the particles in space, just as the sun is. And here's the layers of temperatures. And remember I told you it's extremely hot out here, extremely hot. 1,500 degrees Celsius. And right below, the dipole turns into minus 80 degrees Celsius. There's thousands of degrees temperature difference. And it's hot out there. It's not supposed to be hot. Well, guess what? Because it gets cold here, it gets hot down here. Down here, it's hot on Earth, and that's the hotter it gets here, the colder it gets here, the colder it gets here, the hotter it gets on us. Simple as that. And it's because of the scrub. We're spinning through space, and I got a little GIF of that right here somewhere. Right there. This is exactly what's happening. Now, we are on the arm of the Milky Way, and it's pulling everybody this way. Everything. And as we trail the sun, its particles are scrubbing off all over the place. And that's called a solar wind. They know that. Those particles are everywhere, and we're flowing through those. Not only are those particles just saturating space, and they're everywhere. It's just not here. The light itself is particles. I just showed you that. Light itself is particles. And here are those particles right here. And the black one is the mass that you are standing on right now, because there's nothing but light, and the mass is the black. The white has no mass. That's just energy. I can't find any mass whatsoever. Same particles they found at Fermilab, CERN, and I've interacted with these people, both of them. And all I have found was, CERN, and I didn't actually work with CERN. I went to University of Geneva online and interacted with the professors. I showed them all this stuff about the CMOS and how well it would work with what they're doing. I don't know if I was the cause, but they did shut down CERN for a couple of years to use this same technology, because you can see this without interfering. It's the only way you can see these and judge what's going on without interfering with it. Otherwise, you got to put energy in or take energy out. That's called the observer effect. It destroys the evidence. So now, I have been put in a position where they say because Roger proved there was giants and monsters on this earth and dragons, that means the earth is flat. So they immediately, 15 years ago or 12 years ago, approximately 12 years ago, if you look it up, 12 years ago, it was all started flat earth, because they came after me. And at that point, it just became a flat earth channel. And then it was just I turned into the biggest moron on the face of the planet. And it's never come back. They got me boxed in, and they don't put me out into the general public because I'm false information, because academia has suppressed me. And I attribute most of that to the flat earthers attaching themselves to me. So I don't want it anymore. I'm just telling you right now, I've become bitter, and I don't mean to run on about this, but it's done. Now, the scrub we're having here at this zone is the cause of our increase in temperature. All right? Because we're spinning here thousands and thousands of degrees out here. On Earth, it's 100-ish, a little more. But thousands, why? Same thing here, millions out here for the sun. And it's only 10,000 on the surface. They have calculated. Whether they're right or not, I don't know. But I know it's nowhere near what it is out here. Out here, and I can show you in the eclipse. This is a solar eclipse. Now, what do you see? Stop and take a look at it. I'm going to tune it in here. All right, so I've shown you what is really causing the global warming is the expansion of the atmosphere, and the expansion of the atmosphere is from burning, combusting things that are solid into things that are gases, and expanding the envelope. Now, the only way out of this is to stop burning. When they say pump, baby, pump, burn, baby, burn, yeah, we're going to burn, but it's not going to be in a good way. We need to use and recycle electrons. This is just recycling the electrons. You use them, they come back, you use them again, and they don't do anything. All they do is power things. You get some heat here and there, but just not much. Absolutely nothing like combustion. And what you do is you get these electron showers coming through here, just like they say at CERN, and the muons bounce back out. The electrons go from very low energy showers up to high energy showers. And they can go way, way up. The way they claim, we're talking hundreds of times more energy out than in. That means free energy. And if you could carry it around in a little container like that, this is a Geiger counter that I just made a little mock-up. You could have any kind of AC, DC, USB, 60 cycle, 50 cycle, anything you wanted. Once it's in here, collected up in here, you can do anything you want with it. You put it through, a little regulator, some circuitry. You need a good floating ground. You need somebody that knows how to engineer this stuff. You need a couple designs on a Venturi until you get it right down perfect. You need a different pulses, and then you need different frequencies. And then you need a new type of receiver here, which is not. This is simple stuff. Simple. They have them right now, perovskites, and I think if you took just like spray paint, you sprayed one layer and then the next and the next and the next and the next, and they would relate to different frequencies of light. And the one way in the back would absorb the long frequencies, and the one way in the front would absorb the real short frequencies. And then you can get them all. Right now, I don't think they're collecting too much from the sunlight. Wow, I think I just made a revelation here. I got these pics from a friend in New Zealand who does not want to be into this anymore. It appears I can't get any contact now. So these were taken with a cell phone. And he took, oh, I don't know, half a dozen pictures. There was several of them that were very good. And now, light going through this, there's absolutely zero possibility that it goes the same speed forever. There's no question whatsoever. There's just tons of particles in its way, and it's going to be blinking on and off. It's called the quantum foam. It's fully understood. There is no empty space, and light is a particle, as I just showed you. All right, these are particles of light, and when they hit things, they concuss, and when they concuss, we made it speed up, but they normally slow down. This is a speed up because of the Venturi. And that's not supposed to be allowed either. You're not supposed to accelerate light. You're not supposed to split the black from the white. Well, you should be able to, but they can't. The only way they can do is smashing things, and they find these little bits. But we see them actually divide at the Venturi. So only the white comes through. Shown this so many times, it's just frustrating as hell. And these are the ones, and this is 10 years ago, or more now, from Fermilab, and I tried to interact with them. I showed them this, and they blocked me and called me names. I'm telling you, this is really a disgrace. This is from NASA and all the big guys. This is what they show you for gravity waves. They can't even see them. They don't. This is a theory. Well, we think this might happen. Well, they got a black one and a white one. Why are they showing that? That's because it's a dipole and they're interacting together. Well, guess what? I can show you a real dipole. Now, I just showed you this one here from, I think from probably NASA. This here, whew, that's a mess. That's our immediate solar system. You want to see that? And then I'm going to show you something, a dipole that it just came to me. I think I just learned something. Now, the moon, well, you've seen all this before. Light does not go through there at the same speed. So Webb telescope is just a waste of money. They judge everything they do, on the speed of light. It never changes. No, it doesn't slow down. It goes forever. And that's why they say the galaxies and everything's pulling away from us faster than the speed of light now. It's just because they can see further into particles that are getting slower and slower and slower. They're almost just barely moving by the time they hit us now. So it's a mess. The cosmic microwave background is nothing more than light particles that just stop. They just stop. They're just floating around out there waiting for something to bump into. That's the cosmic microwave background. And there will be black holes in space, yes, because there's dark matter and the white collects around it and the black hole will get bigger and bigger and bigger because there's black ones and white ones everywhere. And this was done in space by the Russians. That was 10 years ago. And this, I tried to interact with the Russians and Fermilab. And Fermilab, Don Lincoln, was kind of nasty. And the Russians just didn't respond. So this is exactly dipole electron flood theory. I said, I know what's going on here. Will somebody talk to me? All right, check this out. This is, I think I got a new theory on this now. I could be wrong. I think that might be the sun, but I don't know. This, again, came from a guy, he just doesn't want to be involved anymore, so I don't want to involve him if he doesn't want to be involved, and I can't get through to him, so. Black and white, that's a dipole. Now, the sun is a dipole. Now, could he do that with the cell phone? I don't know. But this isn't just, that's about as dipole-ish as you can get. And that's the most intense dipole other than possibly Venus. And originally I thought this was Venus. And the reason I thought that is because Venus, it rotates backwards instead of the way all the rest of them do. It goes backwards. And this looks like it has two magnetic fields. You see this one down here? It follows the same pattern, only it's a different field. Venus is going around the solar system just as we are, but it's turning backwards, and we're all turning like we're rolling around, and this one's going backwards. So it's like scrubbing harder and harder, which would give it a bigger magnetic field. So that, originally I thought that was Venus, and it probably is, as the morning star. I would go back to Venus. I'd like to see what, well, here, let me show you what the sun looks like on the eclipse. Maybe I showed you this. Hold on. No, I don't think I did. Well, I think I started to, and then I didn't. So I will conclude that now. What are we looking at? Well, this is the moon, and it's sitting on top of the sun. A total solar eclipse, and this is about as good as it gets. Now, this plane right here, straight across, that's the pole. So let's call this the North Pole, and that's the South Pole. So it's spinning this way. And you say, how do I know it's spinning this way? Why wouldn't it be spinning this way? I know it's spinning this way, and I know it's moving that direction. You say, oh, come on, Roger, how can you tell? Well, let's think about it. I'm saying everything is moving in this direction, including the sun, and the sun is spinning this way. Now, think of what's on the sun. Let's go to the sun. Hold on, sun coming up. All right, I'm going to show you right from this little pic here. The sun is spinning and moving in a direction which would make it scrub more. I showed you this. So the sun is moving in a direction like that, and it's spinning this way. That's why it's scrubbing the stuff off of this side. You see this side? Oh, stuff scrubbing off of there? That means that it's spinning this way because this is the most interaction. This side sloughs off. Now I'm going to show you what it does look like in a solar eclipse, and that's exactly what happens. So once again, my claim, the sun is going that way, spinning like this. Even they go this way, they spin always on their pole. You see the red spot? You see the red spot? See the red spot? That's like extreme scrub. These are like, they set up their own individual fields to keep each other away. See how that one's pushing this one away, and this one's basically pushing that one away, and they got these divisions between them, and it depends on where they are. Because they're on the equator, there's the most intense spin. Way up there, there's very little scrub, very little down here. That's why the poles of our Earth, it's freezing in these two spots, because there's almost no scrub. Just barely, it goes like this here. This one goes, scrubs around like that. This one goes, same thing down here. That's why you got so much cold there. There's not as much scrub. But now we got some polar vortexes. You look up at what's going to happen in the next week, the inauguration of Trump. It's going down to bazillion degrees below zero, or, well, you know what I'm saying. It's going to be cold. I think they said 20 degrees or something like that down at the inauguration. And it's because there's a polar vortex been sort of pushed up into here. And now it's being pushed down. It's going to come around and wrap around the Earth. Anyway, getting back to the scrub. It's going this direction, and this is like coming back, and this is coming back as well. This is the trailing edge coming this way, and there's no brightness. So we know we're going that direction, and this is the trailing, and this is the, and this is the, and here it's a beep, 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 and this is a, it makes sense if you just think about it. Because this space is not, it's just saturated with everything. Every light particle is a particle. You see this? And all the solar wind, yeah, we got all this stuff. Oh, yes, a total vacuum. Yep, no problem. Light never slows down. Well, that is insanity, because this is what light has to go through. I'm telling you right now, we have no idea where we are in space, and some of this stuff looks like it could be very, very much closer than we're being led to believe, such as the Pleiades. What's going on there? That's the same guy who took with the cell phone. And I believe this is the Pleiades. And again, dipoles. You see the black and white, black and white, black and white. And there's some kind of a structure to this whole thing that is like creating one molecule almost, you could see it as. There's a lot of them that are just single little bops here and they're all by themselves. They do interact, but not like this. This is a very strong interaction with almost like a secondary, like the black is sort of going this way and the white is sort of going this way as a globular cluster. Very strange, very, very strange to me. And this is the moon behind it. Now, is it behind it or is it in front of it? I don't know. Where's the Pleiades? They're supposed to be a zillion miles away. I don't know how far they're supposed to be, but I believe that's them. Okay, we're talking about Dirac neutrinos. Are they neutrinos? Yes. Neutrinos can be Dirac particles. Well, they are Dirac particles. They're either Dirac or Majorna, depending upon the size. Well, actually, it's depending upon the mass, and that depends upon the interaction. And the Dirac is really like a photon particle almost. And the lower Majorna is as it's building, basically. That's how I see them. And they say they have flavors and da-da-da-da. And then they're talking about helicity, which means one direction this way or the other direction, but still going in the same way. Spins this way or spins that way. I believe there's only one, and it's the right-hand rule. They spin this way as they go that way. And I will show you why I can demonstrate that, and then I can show you one that didn't follow that and did not end well for that particle. You see this? They always thought there was neutrinos and antineutrinos. Now they say, well, they might be the same, because they violate all these other rules that they have, lepton numbers and all that stuff, because they're just not true. It's a black one and a white one, case closed. Now, neutrinos electrically neutral, well, when they're sitting around, their electric charge can't be used to distinguish them from antineutrinos. They're the same thing. They're exactly the same thing. It's basically upspin and downspin. I'll show you. Instead, experiments have confirmed that neutrinos have a small mass. Yes, they do. But it's not zero, but it's small. I agree with that. All right, they say the neutrinos are the smallest things that exist, and I agree with that, as far as I can determine, although we did find something that's a little stranger. This they call matter, just the opposite. This is the energy. This is the matter. All right, and they're opposite. I agree with that. The white one is the energy. It can get big and it can get almost nothing. The black one never changes. It's always going to be that size no matter what happens. And it's solid matter and it's cold. It gives off no heat whatsoever. This one gives only heat and it has no mass. So it can get huge or it can get tiny. It can get down to almost like, I would say like the tip of a pin of a point. I don't know if it has any mass at all there. This has mass. Now, when they're building mass, they're sort of flipping and flopping around so they don't know where they are. They're half grayish and so forth. Now, that is right from Fermilab. Now, what else came from Fermilab? Well, this came from Fermilab, right there. These are the two particles. These are the Fermilab Dirac neutrinos. Just what I just showed you. Now, they started with huge protons, which are gigantic things like this, and smashed them into little bits. These are the little particles they found. We used light, and we could see them exactly as they are, and then we could create the electron showers from them by putting them through the Venturi. So these were particles through a Venturi that's so tiny, the black is just too big. The Venturi is like this size. When it hits, the white ones just squirt right through, because they can get small or they can get big. It depends on what the fields can crush, and they can get bigger. And when they hit the Venturi, they crush and they squirt right through. The black one just hits and goes bang, 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 bang. It says, I can't get through. And it slaps the white ones through. And then you end up with electron showers. First of all, it accelerates the light. That's not ever supposed to happen. Light is any speed it wants to go. And actually, I had the thing about today about sound. They're talking about sound in outer space. You can't hear sound in outer space because it's a vacuum. No, it's not a vacuum. And yes, you can hear sound. But you can't hear it right close because the sound waves are so long. They say, oh, well, they work with radio waves. That's nothing more than sound waves. They're just a little bit above sound. They communicate with radio waves out there. Yeah, because sound is everything there is. Tesla was exactly correct. It's vibration and frequency. A very long frequency like that is sound. A short one like this is radio waves. A shorter one like this is visible light, and a short one like this is infrared or ultraviolet. It's just, and that's these right here. So if I want to show you what, and I can show you this actually, I'm going to do it. Why not, Roger? Do it. Show them. Show them. Show them. This is what happens. That's light. That's light. And you see how it circles in a circle like that? Well, why is that? It's because it's going through a Venturi. And it's spinning. And they all spin to the right. And how can I say that? Because this is just like a drill bit. And it's spinning here, and it's banging here, and sliding over the top, and boom, over here. Bada boom, bada boom, bada boom, bada boom. And they're all over the place. It's not just one of them coming down here. They're just thousands and thousands of particles. And they all have to crash into this Venturi like that, and then they splay out on the other side. This is the other side on a wall. As a matter of fact, Rod had a Nike box underneath here, see? Or shirt or something. This was done just with... I have the parts. Whoops, I have the stuff here. Same thing he has. The Samsung Galaxy S3 phone from 2012. This goes back many, many years. This was way over 10 years ago. And so anyway, here's what happens. Friction is just more than you scrub something, and it's very, very, very long waves. You can, if you can hear it, is sound. Well, sound starts to move up. So sound is down here, bang, and you hear it. Well, as it gets faster and faster, it becomes a radio wave. And then when it spins faster and faster and faster, it's down in a microwave. And a microwave that works with your kitchen appliance microwave vibrates at exactly, hits the water molecules. It shakes the hell out of the water molecules. And that's all it's doing is blah, and then they heat up. Now, a little higher than that is infrared. And what is infrared? It just warms you up. You can feel it. It warms. It's another bouncer. And then you hit the visible spectrum. Now you're outside of the bouncy area, and you're into these frequencies that come out to be light. Then you get into ultraviolet. It's pretty zip. And then you get into, they have a certain place that's called ultraviolet catastrophe. And at that point, there's no more white particles left. It turns just nothing but X-rays and gamma rays, which is nothing more than black particles left. All the white ones are stripped off. Because it gets hotter and hotter and hotter and hotter and hotter, and it's right down to zero. Because the black ones have no energy whatsoever. I mean, no heat. And that's the ultraviolet catastrophe. Up, 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 and just like that. Everything makes sense when you understand dipole electron flood theory. There's two parts to every particle, the black and the white. They can separate, but they are stuck together just as hard as they can eat. But if you spin them fast enough, the white will take off, and you'll be left with just the black. And it'll be cold. Okay, I've shown you that we created electron showers from the same particles as CERN and Fermilab are using, only we did it from light, and we created electron showers and separated the white from the black. increasing the value of energy exponentially. Let me show you what they do say from these particle collider places. All right, listen to this carefully. The electron volt range of neutrino energy, which I showed you, the black and the white ball, depends on their source and the process producing them. Neutrinos are typically produced in processes involving nuclear reactions. We are in the nuclear range because we're light. That's down where nucleuses are made of, is that light. All right, so we are down in that range. So it involves nuclear reactions where we are. The particle decays, it breaks in half. High energy cosmic events, and here's a breakdown of typical energy ranges. Now listen to this. This is staggering. If my design works, we're golden. Low energy neutrinos, they're still energetic. Solar neutrinos, these are the things coming out of the sun. Those are pretty powerful. They primarily, electron neutrinos, produced in nuclear fusion reactions within the sun. They typically range from a few thousand electron volts to a couple of million electron volts. Now that's pretty energetic, as a, for a particle. Then they go to nuclear reaction. It goes up to typically 2 to 10 million electron volts. That's from a nuclear reactor. Now listen to this. Supernova goes up to 1 to 10 mega electron volts. Now you get into the real stuff, which is gigavolts. All right, so you got atmospheric conditions with cosmic rays. You can get up to a few gigavolts, giga electron volts to tens, which is pretty high. And they're digging an ice cube experiment, which is spending billions of our dollars wastefully. I showed you these exact particles, and listen to this. Accelerator neutrinos, the ones I showed you that Fermilab and CERN created, the same ones I showed only using light. Neutrinos produced in particle accelerators, such as those at Fermilab and CERN, typically have energies in the billions of electron volts, from a few billions to tens of billions, even trillions sometimes. See, high energy neutrinos, you can get up to the trillions. That's 1,000 billion electron volts. And we started out with mega electron volts, basically. It doesn't take much to run those lasers. So we have expanded the energy at absolutely stunningly a large amount. That's my point. If we could do this and get these kind of things, look, summary of typical energy ranges. Solar neutrinos. They're just coming at us like light, thousands to millions. Reactor neutrinos, they're a little higher energy, 2 to 10. Supernova, 1 to 10. Atmospheric, few gigavolts to tens gigavolts. These are atmospheric with cosmic rays. Accelerator ones are gigavolts. These are at CERN and Fermilab. High energy astrophysics is we're in that high energy. We're completely separated, the white from the black. 100% separation. All right, I'm just going to run through them, just pointing to these. I've shown you these. You can go back and look at it again. These are the neutrinos. All right, there's one of them that's just energy and one of them just mass. These are the ones from Fermilab. I showed you we produced the same ones and we divided them to the black and the white, and we should be able to, I think, get free energy from them. Now, this is what the photons look like. I don't know if I showed you this up real close. This is a photon. That's exactly what they look like. The black and white and black and white, 2-bar magnets. And there's a field around it that's very large. And before they turn into photons, they are flavored neutrinos. This was just getting ready to flip. It's charging up and it's going to go blip. Instead of being a downspin, it will become an upspin where the white will be in the front. Now, I have the red ones too. The red ones are the same. All a photon's a photon. The white and the black is the muon and the electron neutrino. Now this one here is a downspin, and this one here is an upspin. See it? Come in this direction. And of course there's the muonish flavors. And then there's a backlash as it hits here, but this is because it's being accelerated. These are all up in here too, but you don't see them because it's only straight in the dead line with the Venturi. Now, this I showed you, light spins, and it creates these repulsion patterns. These are not floppy waves. This is a spin going this way, this way, this way. Sometimes they come that way, sometimes they come over this way, but they're all trying to get away from each other. So look at how elegant these patterns are. They just want you to stay in your own line, I'll stay in my line. And that's just amazingly elegant. Rod did the most absolutely stunning work. Look at this. These are Higgs fields. You should look up what CERN shows for a Higgs field. You know what? I'm going to just show you because it's kind of funny. See this? I said, where's some Higgs field pictures from Fermilab? There are no direct pictures of Higgs field from Fermilab or anywhere else. That's not true. I just showed it to you because it's an invisible field. No, it isn't. You can find visualizations and diagrams depicting its concept. Well, let's go see what they think it looks like. You see this? Here's what they're doing. They're taking huge things like this, which actually are things like this, and they're hitting them head on. Boom. And they just splash things all over, and they see these fields, these round fields, sort of. This is just an artist's rendition, but they see these fields that are from these collisions, and they are normally sort of roundish, and they call them Higgs fields. Well, I show you Higgs fields on steroids. There's no pictures. There's some pictures. That's Higgs fields. Those are Higgs fields, and they come right out of our Venturi, and they are light fields. Higgs fields are nothing more than light fields, and I can say that with absolute certainty. Here is light from the pulse laser. It's just starting to accelerate. You see the field that it's making, these waves? The particle's in here, and it's got a field around it like this big, probably about that big. And it says, I'm coming through with my field. All you guys get out of the way. So they start glowing. Back here, there's no glow because it was going normal speed of light in this atmosphere. But now it's taken off. That's why it's glowing. Back here, right back here, you still got light, but it's just barely starting to increase. Now it's really flowing. Now, as it goes forward, it really takes off. And here it is taken off somewhere here. Right here. So that's the particle. It's still in its full construction here of the black and whites together. And it's flowing through here faster and faster and faster. It's pulling itself out of its own magnetic wave, just exactly like a jet fighter does when it breaks the speed of sound. We're getting faster than its own magnetic wave can plow through all the other magnetic fields in front of it. So it's just pulling itself right out. And it's really completely out of a magnetic field here. It's just an incredible amount of speed. And then you have the nuclear explosion. And you say, oh, come on, Roger. Yes. It's a subatomic nuclear because it's smaller than the nucleus. Everything is made of these particles, so it's a subatomic, smaller than an atom, which is in a nucleus, nuclear explosion. And what happens when that nuclear explosion goes? You have light continues this way, and all the mass that it can go with it. In our case, not much mass is coming, depending upon how the Venturi is. Sometimes a lot of mass, sometimes very few, a little bit of mass. But there's light and mass. The other here, light bounces back, and it bounces back with a vengeance. That's why these are lit up. The whole thing is just because it exploded, just like an atomic bomb will explode. All right, I guess it's about time to stop. And this is, if we can do this and get the kind of energy they're talking about, this zillions of volts more than you put into it, this is increased high energy coming from low energy. As simple as that. And you saw the numbers, they're just staggering. If you could carry something around like that, never have to plug it in. All you got to do is turn it on. Once you turn it on, it creates its own showers. That's all I can tell you. And if you're going to do, maybe you would have to have a solid ground if you were using extreme amounts of energy, yes. because that could create a lot of energy, and you need a floating ground to bring it back to itself. It's a little bit confusing, and I haven't been doing this for many, many years. But normally you ground it to Earth in case something goes wrong. In this case, if you were holding that and if something did go wrong and it had to jump that electricity out of there, you would be the conduit to ground, and that would be an unfortunate day for you. But if you, this is simple. It's simple. I'm just telling you, I can't do it. But it is simple for somebody who knows what they're doing. I understand the concept of the increase in energy, and you do too. You just saw it. They say, if you can create these neutrinos, these different levels of neutrinos, which we created pure, raw, white electron neutrinos, not partial neutrinos. We created 100% electron showers. That, to me, is the top end. It could be many billions up to trillions, coming from millions. That is just a staggering increase in energy. And that's what they're doing right now at CERN. They're doing high luminosity, they call it. It's the LHC high luminosity now. Anytime you create light, it's energy. The brighter it is, the more energy. And that's just a fact. Anybody can dispute that? I'd love to hear them.